Class 11th Chemistry, Unit 12, Organic Chemistry, some basic principles and techniques, and in this video we will discuss about structural representations of organic compounds. Structures of organic compounds are represented in several ways. Lewis structure or dot structure, dash structure or complete structure, condensed structure, and bond line structural formulas. About Lewis structure or dot structure, which we have discussed in the chapter chemical bonding and molecular structure. Okay. Now, in Lewis structure, we represent the electrons by dots. If shared pair of electrons are replaced by the dash, then we will get the complete structural formula. For example, this is the complete structural formula of ethane. This is complete structural formula of ethene. Okay. There is double bond between carbon-carbon. This is the complete structural formula of ethyne, triple bond between carbon-carbon. This is methanol. Okay. This carbon is attached with the 3 hydrogen atoms. And this carbon is also attached with the oxygen, and this oxygen is attached with this hydrogen. All bonds are represented by dash. Clear? Now, if these dashes are removed, then we will get the condensed structural formula like this. This is the condensed structural formula of ethane. Okay, we can say on this carbon atom, 3 hydrogen atoms are attached. So we can write this is CH3. The same way, this carbon atom is also attached with the 3 hydrogen atoms. So this is CH3. This may further condensed as C2H6. Clear? In the same way, this is the condensed formula of ethene. And this may further condensed as C2H4. And this is the condensed formula of ethyne. This may further condensed as C2H2. And this is the condensed formula of CH3OH, that is methanol. Clear? In the condensed formula, we will not write the single bond. We will not mention the dash for single bond. Clear? Now, bond line structural representation. In it, carbon and hydrogen atoms are not shown, and the lines representing carbon-carbon bonds are drawn in a zigzag fashion. The only atoms specifically written are oxygen, chlorine, nitrogen, etc. That is, heteroatoms other than carbon and hydrogen are specifically written. The terminals denote methyl, that is CH3 groups, unless indicated otherwise by a functional group. While the line junctions, that is where lines are joined, denote carbon atoms bonded to appropriate number of hydrogens required to satisfy the valency of the carbon atoms. For example, 3-methyl octane. This is the condensed formula of this 3-methyl octane. In a straight chain, there are 8 carbon atoms. Okay. So in the bond line, we can represent. So this is first terminal carbon atom, this dot. Okay. Then this is second. This is third. This is 4. This is 5. This is 6. This is 7. And this is 8. This is octane. And at the third carbon atom, there is a methyl. So we can say this is first, this is second, and this one is the third carbon atom. And so this is methyl. Okay. This terminal, this one, and this one. This terminal represent the methyl group, that is CH3. Okay. And this junction, this junction represent the carbon. And these lines represent the bond between carbon-carbon. Is it clear? This is about bond line structural representation. See some more example. 2-bromobutane. Okay, butane means 4 carbon atoms. Like this is 1, 2, 3 and 4. And on the second carbon atom, Br is attached. Okay, this can also be represented like this. If we write in the bond line, then this is first carbon atom, this is second, this is third and this is 4. Clear? And on the second carbon atom, Br is there. So we have to mention Br here. Okay, this is bond line structural formula. You can also start the line, zigzag line from this. That is 1, this is 2, this is 3 and this is 4. And on the second carbon atom, this Br is there. This is 2-bromobutane. In cyclic compounds, the bond line formulas may be given as follows. This is cyclopropane. That is 3 carbon atoms in a ring. Okay. And there is a single bond between these carbon atoms. In bond line, this is represented like this. Cyclopentane. Okay. This is the condensed formula for cyclopentane. And in the bond line, we will represent it like this, pentagon. Then this is chlorocyclohexane. In the ring, 6 carbon atoms are there. So, if we make this hexagon, then this represents the cyclohexane. Clear? And chlorocyclohexane, it means at one carbon atom, at any carbon atom, you can add chlorine. See like this. So, this is the bond line structural representation of chlorocyclohexane. Now see problem 12.4. Expand each of the following condensed formulas into their complete structural formulas. Okay. Now see, first of all count the carbon atoms. 1, 2, 3, 4 and 5. Okay. So you can make 1, 2, this is 3, this is 4 and this is 5. Now on this, now mention the hydrogen atom by the dash. Attach hydrogen atom with the carbon by dash. Okay, on this carbon atom 3 hydrogen atoms, on this carbon atom 2 hydrogen atoms, and on this carbon atom oxygen is attached. And as we know, valency of carbon should be completed as 4 and oxygen makes double bond. So we'll write this. And to this carbon again 2 hydrogen atoms, and on this carbon 3 hydrogen atoms. Clear? In the same way, you can mention this CH3, CH, double bond, CH, now CH2 thrice. Okay, it means CH2 group is repeating 3 times. So just you can mention that is, this is first carbon atom, then this is second, this is a double bond, then this is carbon, and after this carbon 3 CH2 group is there. So we will make 3 carbon atoms and then last one is 3. Complete the valency of carbon by hydrogen, because in this compound only hydrogen atoms are there. So on this carbon atom 3 hydrogen atoms. Okay, this is 1 hydrogen atom, then this is again 1, then on these 3 carbon atoms 2 hydrogen atoms are there. Clear? And on terminal 3 hydrogen atoms are linked. This is complete structural formula. Now problem 12.5. For each of the following compounds write a condensed formula and also their bond line formula. Okay, now just see, this is HO, then CH2, 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 then this is CH, CH3 is attached to this carbon. Okay, then this CH, and to this carbon two methyl groups are attached. So in the condensed form, we can write this is HO. Now this similar groups CH2, 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 same groups 3 times. So we can write CH2 thrice. Okay. Then CH, this CH having CH3 group, and this CH has two CH3 groups. So we can write this is CH3 twice. Clear? Now in this is N triple bond C, this is CH, C triple bond N, and this carbon is attached with the OH. In the condensed form, again you can see this is OH. Okay, then this CH, and to this carbon, two CN, that is this is CN and this is CN, twice is there. So we can write this is CN twice. These are the condensed formula. Now, then in bond line formula, how can we represent? Now just come to for this bond line formula. Now just again calculate the carbon atom in a straight chain. So you can say this is 1, this is 2, this is 3, this is 4. Okay, this CH3 is attached with this. This is 5. Okay, and this one is 6. So you can start like this. This is 1, this is 2. Okay, 2 carbon atoms. Then this is 3, this is 4, this is 5, and this is 6. You can also start like this. This is 1, 2, 3, 4, 5, and 6. Now on the first carbon atom there is OH is there. You can write this is OH. Clear? In this way you can write this is OH. And then on fourth carbon atom there is methyl group. Okay, so we can say this is 1, 2, this is 3, and this is fourth one. So this is the methyl group. And in this case, this is the fourth carbon atom. So this is methyl group. And on the fifth carbon atom, again there is the one methyl group. In this is the fifth carbon atom. So this is methyl group, and in this is methyl group. Both are the correct bond line formula. The same case for this central dot, this junction represent the carbon, and to this carbon 3 groups are there. One is OH and 2 are CN. So this is CN and this is CN. Then 3-dimensional representation of organic molecules. Actually our paper is 2-dimension and these organic compounds are 3-dimension. So we have to represent these 3-dimensional form, or we can say 3-dimensional formulas on a plain paper. Then how can we represent it? We can represent these 3-dimensional on a plain paper by using solid and dashed wedge formula. Now what is this wedge? Okay, this wedge is the structure like this. At one end this is thin, and continuously at the another end if we go, its thickness is increases. Okay, this is wedge. The 3D image of a molecule from a 2-dimensional picture can be understood by using solid and dashed wedge. Now again this is the wedge. Now what the solid wedge? This is solid wedge and this is dashed wedge. Clear? Now in these formulas the solid wedge is used to indicate a bond projecting out of the plane of paper towards the observer, and the dashed wedge is used to depict the bond projecting out of the plane of the paper and away from the observer. Again remember, dashed wedge is used to indicate the bond which is away from the observer, and solid wedge is used to indicate the bond which is towards the observer. Okay, wedges are shown in such a way that the broad end of the wedge is towards the observer. The bond lying in plane of the paper are depicted by using normal line. See, this is the 3-dimensional representation of methane. Okay, this is central carbon atom, and this we are observing this methane from this side. So This is the bond towards observer. So we use this solid wedge, and from in this solid wedge, this broad end, okay, this broad end is to the observer side. And these two normal lines represent the bonds in a plane of paper. And this dashed wedge, this represents the bond away from observer. Clear? Then molecular models. Molecular models are physical devices that are used for a better visualization and perception of three-dimensional shapes of organic molecules. These are made of wood, plastic, or metal and are commercially available. In the market, these are available. Commonly, three types of molecular models are used: framework model, ball and stick model, and space filling model. Clear? In the framework model, only the bonds connecting the atoms of a molecule and not the atoms themselves are shown. Like see, only bonds are shown in framework model. Atoms are not shown. In the ball and stick model, both the atoms and the bonds are shown. Balls represent atoms and the stick denotes a bond. See this. This is the ball and stick model of methane, CH4. This is the carbon and these are the hydrogen atoms, and these sticks represent the bond between carbon and hydrogen. Compounds containing carbon-carbon double bond, for example ethene, can best be represented by using springs in place of sticks. See this one. Okay, and these models are referred to as ball and spring model. These springs represent the double bond. The space filling model emphasizes the relative size of each atom based on its van der Waals radius. In this case, bonds are not shown in this model. Only we will show the atoms. It conveys the volume occupied by each atom in the molecule. Okay. See again, this is the methane. This is the carbon. And 1, 2, 3, and this one is 4. These spheres represent the hydrogen. This is space filling model. Okay. Thank you. Subscribe my channel to get the next video of this chapter.